All right, hello everybody. Let's continue looking at section 6.3. So we've talked about some of the theory of the inverse trig functions, and we've talked about just sort of the basics of how you would evaluate them either from the unit circle or using a calculator. So next, what we're going to get into is using these to solve for missing sides or missing angles of triangles. They have kind of this breakdown here for you. And I guess what I would just say is just remember the basics of SOHCAHTOA, because that's really all that this is derived from here. So your basic trig definitions, sine of the angle, that's the opposite over the hypotenuse. The cosine of the angle is going to be the adjacent over the hypotenuse. And then the tangent of the angle, that's going to be the opposite over the adjacent. And so that's what SOHCAHTOA is trying to help you remember. You've got sine, opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite adjacent, so ka and toa. And so when you're doing a problem like this, the two sides tell you which to use. So what I mean by that is that for a particular problem, let's say, for instance, I know the adjacent side and I know the hypotenuse. Well, if I have the adjacent and the hypotenuse in a particular problem that I'm using, that would tell me to use the cosine, or in particular the cosine inverse, because the adjacent and the hypotenuse are the two sides that they tell me, the two sides that I know. So that's usually how these problems are going to fall out, where you're going to know two of the sides of the triangle, and based off of those two, that will kind of guide you into which trig function you're going to want based off of SOHCAHTOA. So let's see this in action here, shall we? So here's a triangle. There it is. In all its glory. We have an angle theta. They want us to find angle theta. So if we look at this triangle, what we will notice, 9 down here, this would be the adjacent side of the triangle. This is across from the right angle. So this one right here is going to be the hypotenuse. So if you go by SO, Ka, and TOA here, what you will notice is I have the hypotenuse and I have the adjacent. Those are the two sides I know. So if we look, here's the adjacent, here's the hypotenuse. The cosine is what I need to use. So we're going to use cosine. So what that means is cosine of theta is going to equal the opposite over the adjacent. So that's going to be 9 over 12. And if I want to solve for theta, I need to do the cosine inverse of 9 over 12. And then what you can do is get yourself a friendly neighborhood calculator and do second cosine, 9 divided by 12. And if I put that in, that'll give me 0.7227. And that's in radians. 0.7227. If you want it in degrees, you can the calculator you're using over to degree mode. So if you switch this over to degree mode, you can find the angle in degrees. Typically with word problems, that's like the one situation where we actually want degrees. Most of the time in trig, we like to do things in terms of radians, but a word problem is like the one situation where degrees are like, okay. So the degree equivalent is 41.41 degrees. So depending on what units you're operating in and what you're asked to provide, you can switch the mode of the calculator you're using and provide whatever it is that you're after. Again, don't forget SOHCAHTOA. And then just like I said, the two sides that you know that can guide you to which trig function you're going to want for any particular problem. Here's another one. So here we've got our triangle. We're trying to find angle theta again. Here we're across from angle theta. That is the opposite side. Again, we're across from the right angle, which makes this one the hypotenuse. And so if we go back to SOHCAHTOA, you will notice that in this problem, I have the opposite and I have the hypotenuse. So opposite and hypotenuse tell me I need to use sine. So then what this means is that the sine of theta is equivalent to 6/10. If my goal is to solve for theta, to find an angle I don't know, that's what the inverse trig operations are for. You have sine inverse of 6/10. And let's see, I'm still in degree mode, so I'll give you the degree one first. Sine inverse of 6 divided by 10. That is 36.87 degrees. That's approximately what it's equal to. So 36.87 degrees. That is the value of theta. If you do it in radians, we'll switch this calculator back to radian mode. And that's the same as 0.6435 radians. So depending on which units you are asked to provide, you can either give one or the other. So that is that's theta. That's theta is what this equals. One other thing I will point out to you as well. Sometimes you see arc sine, arc cosine, and arc tan. And these are just equivalent. They mean the same thing, but they're just different ways of writing sine inverse, cosine inverse, and tan inverse. So if you ever see like arc sine, that means, so like for the problem we just did, you could write it as arc sine 6/10, and it means the exact same thing. It's just another notation. It's a thing. It exists. You see it every once in a while. I think the reason it exists is because with the negative ones, people might get confused as to whether you mean reciprocal or inverse. You know, when you say sine -1, do you mean the inverse sine, or are you actually talking about the cosecant? And so to just try to clarify that, it's another notation you sometimes see. So it's a thing. If you see arc sine, don't have a big freak out. It's just another way of saying sine -1, sine inverse. They mean the exact same thing. Just be aware, it's a thing. You might see it once in a blue moon. Okay. So here they're talking about compositions and what happens if you compose a trig function with its inverse. And fun fact, composition with inverse trig may put you in a different quadrant. And if you're not altogether sure what I mean by that, bear with me and when we go over some examples, that'll maybe make more sense, like what on earth I'm talking about and why it's even a thing. But that's sort of what this is driving at here. This is just going back to the limitations on which quadrants the trig functions are defined for. So let's look here. So let's look at this first one. So you got pi over 3 here. Now pi over 3 is in quadrant 1. Here's pi over 3. It's in quadrant 1. I don't know why I'm starting to write a Roman numeral 2. Let's try that again. Here we go. We're in quadrant 1. Pi over 3, 180 divided by 3 is 60. So the one across from 60 degrees is root 3 over 2. And so fun fact, if you do sine inverse of sine pi over 3, what you will get is just pi over 3. Because what these are basically doing is they're inverses, so they're canceling each other out. And what's left is the angle that you started with. Because you're basically saying, okay, sine of pi over 3 is root 3 over 2. So if I do sine inverse of root 3 over 2, that's just going to take me back to the angle I started with, which was pi over 3. Now, in some cases, they're going to cancel out and it'll work out nice and neat like that. But there are other situations where it's not going to work out quite so neat and tidy. That's what we're going to see in part B. So here we've got 2 pi over 3, which is this angle actually that's over here. So this is 2 pi over 3, also known as a 120 degree angle. So here, again, the sine is root 3 over 2. So if you do sine inverse of sine 2 pi over 3. And like I said earlier, this is quadrant number 2. Sine of 2 pi over 3 is root 3 over 2. And fun fact, sine inverse of any value must be in quadrant 1 or quadrant 4. Being in quadrant 2 is a problem. So the sine inverse of root 3 over 2, we actually found that earlier. That's this. So really, it turns out that the answer is going to be pi over 3 again. Because being over in quadrant 2 is not a valid answer. What you need is an equivalent. What you need is an equivalent angle over in quadrant 1 that gives you the same value for sine. That'll give you the same y value. That's the same height. So That's why this is kind of a big deal. And that's what I meant earlier when I said sometimes, not always, like what I actually said. It may put you in a different quadrant. It may put you in a different quadrant. That's what I was getting at when I said that. Even though in this problem, the angle starts in quadrant 2, we're limited to only quadrants 1 or 4 for the inverse of sine. Let's go ahead and I'm going to make a copy of this slide to put the other ones on rather than trying to squeeze them in there. So let's go ahead and erase this stuff. All right, so let's look at part C here. So cosine inverse of cosine of 2 pi over 3. So what does that look like? So 2 pi over 3 is going to be over here. We were actually just looking at 2 pi over 3. And this again is in quadrant 2. For cosine, that is okay. Cosine inverse is in Q1 and Q2. So being in quadrant 2 for cosine inverse is actually perfectly fine. As we mentioned, this is across from that is root 3 over 2, and then the x value is going to be negative a half. So this is basically just saying cosine inverse of negative 1/2. And then if you do the cosine inverse of negative 1/2, fun fact, that's going to take you back to the original value, which is just 2 pi over 3. So normally what often happens with inverses is the cosine inverse and the cosine cancel out. And what you're left with is just 2 pi over 3. And it gets you back to where you started. That isn't always going to be the case, though. So if we look at part D, what you will notice is that we have an inverse cosine of negative pi over 3. So we're going to have this angle right here, negative pi over 3. And this is going to be positive a half right here. And this is negative root 3 over 2 down here. So what you will notice is that I am in quadrant 4. I need to move up to one of the legal quadrants, either 1 or 2. In this case, it's going to be quadrant 1. So what I'm going to have is this right here. And so this is actually going to be positive pi over 3, which will be the corresponding angle in quadrant 1. So the cosine inverse of cosine of negative pi over 3 is in fact going to equal pi over 3, because a negative angle is not valid for or a value that's in quadrant 4 is not going to be valid for cosine inverse. All right. What else do we have going on here? Whoop, that was a little too far. Okay. Evaluate tangent of tan pi over 8 and tan inverse of tangent of 11 pi over 9. Okay, well, so tangent is in quadrants 1 and 4. So tan inverse is in Q1 and Q4. All All right, the first angle is pi over 8. And pi over 8, I can tell you, is going to be right there. This is pi over 8, which is in quadrant 1. So if you do tan inverse of tangent of pi over 8, since you're in quadrant 1, everything's hunky-dory. Nothing to see here. Tan inverse cancels out tan. And what's left is just pi over 8. Well, there you go. Meanwhile, what do we have here? This is 11 pi over 9. So pi is right here, which would be the same as 9 pi over 9. So 11 pi over 9 is actually going to be over here, like somewhere. This will be 11 pi over 9. And the specific values this equals actually don't even matter really. But this is 11 pi over 9. And what you will notice is that this is in quadrant 3. And so the corresponding angle from 3 is in 1. Why is that? You might remember this. All students take calculus. We are currently in quadrant 3. Q3 has a positive tan. Q1 also has positive tangent values because all the trig values are positive in quadrant 1. So what we need to do is find an angle that is also going to be in quadrant 1, which is going to be like over here. Well, it turns out that that is going to be 2 pi over 9. How do I know? Well, if I do 11 pi over 9, and if I subtract pi, if I do a half turn back to quadrant 1, 11 pi over 9 minus pi is 11 pi over 9 minus 9 pi over 9, which is 2 pi over 9. So then the answer to this one, tangent inverse of tangent of 11 pi over 9 equals 2 pi over 9. And that is the solution. So for sine, what often happens is that if you're in quadrant 2, you got to move to quadrant 1. For cosine, what often happens is if you're in quadrant 4, you got to move to quadrant 1. And if it's tangent, what happens is that if you're in quadrant 3, you got to move over to quadrant 1. That's kind of how it plays out there. That's if they're positive. But anyway, so that is that one there. All right. Here we're mixing and matching them here. So here we've got the cosine of 13 pi over 6, and we're doing the inverse sine of that. Let's first of all try to figure out where 13 pi over 6 is. So if you go around once, that's 12 pi over 6. So 13 pi over 6 is actually going to be like over here. This is going to be 13 pi over 6. This right here is 2 pi, one complete turn, also known as 12 pi over 6. And so if this is an extra pi over 6, that's a 30-degree angle. across from 30 is a half. And let's see here. This is going to be root 3 over 2 for those playing the home game. So we're in quadrant 1. The sign is so let's see here. So cosine of 13 pi over 6 is a half. So we're going to do sine inverse of, or actually, sorry. So whoa. I'm doing the cosine. So the cosine of 13 pi over 6 is root 3 over 2. So then what I need to do is figure out what is the sine inverse where it's a root 3 over 2. Well, if I want a sine value of root 3 over 2, that means I want root 3 over 2 right here, which means I need a 60-degree angle, also known as pi over 3. So then the solution, because cosine of 13 pi over 6 happens to equal root 3 over 2, then if you do the sine inverse of that, that is actually going to give you pi over 3. So the result we get is pi over 3 for that one. So there we're doing a combination of sine and cosine. Here we have another one. So we've got sine of negative 11 pi over 4. All right, let's figure out what that's going to be. So we're negatives, so we're going to have 1, 3, 5, 7, 9, 11. So negative 11 pi over 4 is right over here. And again, the way I remember that, you're going to have negative pi over 4, negative 3 pi over 4, negative 5 pi over 4, negative 7 pi over 4, and you'll have negative 9 pi over 4. And this will be negative 11 pi over 4. So you're just counting odd numbers is what's happening. So let's see. So what is this going to be? This is negative 3 pi over 4. Let's see. So this is negative root 2 over 2, and this is also negative root 2 over 2. Anyone that's over 4 is going to be a root 2 over 2. And since I am down and left, both of them are going to be negative. And so the sign is going to be this one right here. It's the y value. So sine of negative 11 pi over 4 is going to equal negative root 2 over 2. So then what I need to do is I need to do cosine inverse of negative root 2 over 2. Now for cosine, I either want to be in quadrant 1 or 2. And since it's negative, that's going to put me in quadrant 2. So we've got negative root 2 over 2. And that angle right there, that's going to be that's going to be 3 pi over 4. So the solution then is going to be 3 pi over 4. Because that is the cosine value that would, the angle that would give you negative root 2 over 2 for cosine. All right. Find an exact value for sine of cosine inverse of 4/5. Okay. This one, we're going to do kind of a different strategy. And I think compared to what we were doing, you all will probably maybe like this a little better. But again, don't forget your SOHCAHTOA. So this is, say, the cosine. So we want a triangle. So we'll put an angle right here. We want the adjacent to be 4, and we want the hypotenuse to be 5. So here's the adjacent, which is 4. Here's the hypotenuse, which is 5. And again, we're doing adjacent and hypotenuse because we're talking about cosine. So cosine is the adjacent over the hypotenuse. Now this is a right triangle, and you might remember this. No, I don't want the highlighter. But you might remember this. Like this is A, this is B, this is C. The Pythagorean theorem tells you a squared plus b squared equals c squared. So if we're trying to find b, we're going to have 4 squared plus b squared equals 5 squared. I'm going to cut to the chase. You can solve this for yourself, but that's going to give you b is equal to 3. That's a Pythagorean triple, 3, 4, 5, if you happen to know that. But the missing side is going to be 3, which is going to be the opposite side. So if they ask me for the sine, which is the opposite over the hypotenuse, that means that sine of the angle theta is going to be opposite over hypotenuse, 3/5. So we don't even need to know the angle in question. It doesn't even matter one way or the other. If we know the sides that we're referring to, and if we can use the Pythagorean theorem to find the missing sides that we need, we can find any other trig ratio based off of the information that we have. Here's another one that's kind of in this vein. So again, remember SOHCAHTOA. And notice this time around, we've got tangent, and we're going to be interested in TOA. So let us look at a right triangle like so. We'll put an angle over here. The opposite side is over here. The opposite will be 5. We'll call this one A. This is the adjacent side, which is going to be 12. We'll call that one B. And then finally, we have the hypotenuse, which we don't know. That one's going to be C. Use A squared plus B squared equals C squared. That's going to be 5 squared plus 12 squared equals C squared. If you work out what that is, you're going to end up with C equaling 13. So then if your goal is to figure out cosine, cosine is the adjacent over the hypotenuse, which means that the cosine of theta, the adjacent is 12. Adjacent is 12, the hypotenuse is 13. So 5/13. That is the solution to that particular problem. Okay. Evaluating composition for sine and inverse tangent. So this is going to be a very similar sort of setup here. So you've got SOHCAHTOA. So we're starting with tangent again. Draw ourselves a right triangle. Let's see, here is the opposite side. Here is the adjacent side. This right here is the hypotenuse. This is C, this is B, this is A. Let's see, we've got the opposite, which will be a 7. We've got the adjacent, which is a 4. This one will not work out quite as nice and neat as the other ones did, because this is not a Pythagorean triple. Let's see, what is this? This is 7 squared plus 4 squared equals C squared. That's 49 plus 16 equals C squared. What is that? 65, I want to say. And then that means C will be the square root of 65. And so then now we want sine, which is the opposite over the hypotenuse. So sine of theta is going to be 7 over root 65. Now, having a square root on the bottom is kind of frowned upon. So what we will do is multiply by root 65 on top and on bottom. And if you do that, you will end up with 7 root 65 over 65, which will be the solution for that one there. And it looks like we have one left. Let's see here. So again, this is going to be one where the Pythagorean theorem is not going to work out quite so neat and tidy the way the other ones did, but the same approach is what we're going to use. So this time, what do we have? We have sine, we want so. Let's draw ourselves a triangle here. Put the angle down there. So what is this? We want the opposite, which is going to be 7. And we want the hypotenuse, which is 9. That's what so tells us, opposite and hypotenuse. This one's A, this one's C. We don't know the adjacent, which is going to be B. So we know A squared plus B squared equals C squared. A is 7. We don't know B. We do know C, that's 9. So this is 49 plus B squared equals 81. Subtract. And let's see, B squared is equal to, so that 81 minus 49, that is 32. So then we need to square root both sides. And fun fact, you can actually break apart the square root of 32 because that is root 16 times root 2. And fun fact about 16, that has a square root, so this is 4 root 2. So we have the adjacent side, 4 root 2. And we want to have the cosine, which will be the adjacent over the hypotenuse. So we're almost done. The cosine of theta is going to be the adjacent side, 4 root 2 over the hypotenuse, which is 9. And there you have it, 4 root 2 over 9. All right. So that is the end of section 6.3. And let's just, so we'll go ahead and stop the recording there.